Okay, I guess we can start slowly. As always, if you want to, like have some discussions with me on various things or on, this sort of content of today's lecture, then please feel free to do. I mean, I'm sort of also trying to keep a good pace so that we are, in one way enjoying the thing and also in the other way that we are not getting lost into the technical details. We want to see certain big pictures out, zooming out from the outside, and then sometimes we're gonna need to get our hands dirty, zooming in into the technicalities. But I want to really keep a good balance so that you guys are not bored. And also, again, I mean, in my view, the techniques are rather simple yet fundamental, because you see that I don't know, they are quite original in some ways and quite simple in some other ways. And I'm hopeful that they're going to be helpful for you one way or the other. Yeah, so the whole lecture for today can be summarized in the sense that if you go along calibrated curves or backward characteristics in the PD language, then you have differentiability. Yeah, but surely you have to take out the endpoints, because we might not have differentiability along the endpoint. And the theorem we stated last time already, there were two parts of it. We just proved the first part, and we're gonna do the second part. But I mean, let me do a little bit of the restatement of the theorem, an equivalent way of the statement of the theorem, so that you sort of see that, again, it's rather, I mean, you can phrase it either in the dynamical system framework or equivalently in the PD framework. Um, what you have, the first assumptions, so these two statements are equivalent. First assumption tells us that u is given to be a Lipschitz function in the torus, and u satisfies that h of x dux less than equals to c almost everywhere in the torus. That's the first requirement. The second requirement is that let gamma mapping from AB to Tn be uh, be a ULC calibrated curve, or equivalently, uh, you know, be a minimizer, minimizer, you know, of the corresponding action function, right? Minimizer curve. Okay, that's already what we proved, given the fact that u is bounded by L plus C, right? Then we have two statements. The first one we proved already, so this is what we done last time. I'm gonna record very quickly, just in a minute, that we have that if u is differentiable at gamma t for some t between A and B, including the two endpoints, because we assume that it's differentiable, okay? Then we have that we can compute the gradient, du of gamma t, it's just the dual dv of L at gamma t dot. And surely that we are in the fixed energy level C, so I'm not gonna recall the second one, okay? So the main goal for today is exactly the statement I said it, earlier, that u is differentiable along this calibrated curve, except possibly the two endpoints. It might or might not differentiable at the two endpoints. We don't know, but we know for sure that it's differentiable in the between. That u is differentiable at gamma t for all A less than t less than b. Okay, so this is really important that we don't include the endpoints. And again, this is a remarkable result because it's sort of, again, we are using a lot of backgrounds that we have done earlier for this. So you're gonna see that the proof is actually not too complicated, but I can say that this is sort of like the key or the backbones of everything that people want to do, going from, you know, Wickham theory for sure, or dynamical system of Hamiltonian dynamics, or also backward characteristics in the characteristic methods or other methods that we know that if we go back along the characteristics, then the solution to the PD is differentiable. So that is a very important result. Okay. But it turns out that, you know, again, once we have built all the tools that we need, then the proof goes through naturally. So let's do it. I guess that you have a look already in the proof, then you can see that the proof is not too complex. Um, and you know, and eventually, if I have time, I'm gonna also tell you some parts of part one that actually we can do one also directly without using two, with you know, in a different way today as well if I have time. So surely the reference for this is, you can look into this. You know, this is I think the clearest way. Author is also that is in Fatih's book, or it's in my book in a in you know, in the part about backward characteristics. Okay. Um, so you know, the idea is sort of like, the idea is sort of like we have A less than t less than b. So essentially we can approach gamma t from both the left and the right. I mean, like, you know, going from gamma A to gamma T, this is approaching it from the left, or going from gamma T to gamma B, you know, this is approaching from the right. And having those two information, it's important for us to you know, essentially to have two-sided control to get that U is differentiable there. Okay. Um, Okay, so that's the first important idea. Now, what we do here? Oh, I'm sorry. Yeah, so this is just this is. I said that I'm gonna record the proof of part one for 1 minute, but then I forgot. I mean, just to recall the proof of part one in 1 minute. I'm sorry. You know, what we do is just that we know that U is differentiable at gamma t already. So, you know, I'm just gonna approach gamma t. In this case, if t is less than b, then I'm just gonna approach gamma t from some t prime greater than t and approaching t. And you know, because I know it's differentiable, so I can just take this uh, difference quotient. I let t prime goes to t. I get by chain rule it's equal to this one, right? And on the right hand side, I can just use the mean value theorem to get this. Combining the two together, I have this equality, du dot with gamma dot minus L of gamma gamma dot equals to C. And I noticed that, you know, the quantity on the left is less than equals to h of gamma du of gamma. So I have h of gamma du gamma is greater equals to C. Okay. On the other hand, I have the other inequality by the hypothesis, so I can combine the two and get that equality must happen, in which I get that du equals to this, and then h of gamma du gamma is on the fixed C energy level. Okay, so that's pretty much it. Okay, yeah, sorry I forgot. So now let's do part two. As I said, we can, you know, you know, going from above down here, as I said, we can approach gamma t from the left or the right. So, you know, this is gamma I, this is gamma b, and gamma t is somewhere here. Okay, so we can approach gamma t by going from gamma I to gamma t. that's sort of approaching whatever, I mean, going from left to right, or approaching gamma t from the left, or I can also approaching gamma t from the right, like this. Okay, so I need to use both of those information to have two-sided control, and the idea is actually pretty neat and natural, right? We know. So what do we know? So we know that gamma is calibrated, right? Or a minimizer, right? So in particular, we know that u of gamma t minus u of gamma a equals to the action functional on gamma of L plus C, right? So it's just integral from a to t L of gamma s, gamma dot s ds plus what plus C times t minus I. So this is, I'm considering going from gamma a to gamma t. I have that. Now, to see that my function u is differentiable, so let x equals to gamma t. So to see that u is differentiable at x, right? So the natural idea is that I have this is x equals to gamma t. To know that my function is differentiable at x, I need to sort of explore the nearby neighborhood of x, right? I need to see, around x what's going on, right? For example, I'm looking at this point y. How do I see the difference in the value of ux and uy, right? So for y near x, how do I compare the value of ux, uy, and ux? Okay. How do we see that, and how do we read up the information to conclude that u is differentiable at x? And a natural idea is that I have the curve gamma, right? So I have the curve gamma connecting from gamma a to gamma t like that. Okay. Naturally, I'm not saying this is the only way. In fact, you can write out some different variants of the proof. Naturally, to explore y, I can think of trying to go from gamma a to y, right? I can make certain perturbations of the curve gamma, right? So this is my curve gamma, the original curve gamma. Because y is close to x, I can sort of use gamma to make certain natural perturbations to create a new curve gamma y connecting from gamma a to y. And once I'm able to create gamma y, then I notice the fact that for this gamma y connecting gamma a to y, I have a natural inequality because u is bounded by L plus C. So I should have that u of y minus u of gamma y of gamma y of a is just a. So it's going to be less than equals to the integral from a to t L of gamma y dot ds plus c of t minus I. Okay, so I should have said that gamma y is the curve mapping from a to t mapping to the torus. Okay, so this is sort of the heuristic idea, right? I'm trying to create certain perturbations or certain curves connecting from gamma a to y, and then I can use sort of this inequality to sort of read up the information here, right? Because I have that for gamma y, I have this inequality, but for gamma, I have is a calibrated curve, or then I minimize. I have equality. I can combine the two, and having certain information done. Okay, that's the idea. Okay, so now let's have a look into the lab panel here. That exactly the idea I have written down. For y here, we're just gonna create the curve gamma y. That is a combinations of gamma with a with a how should I say this, with a the first part is gamma, right? The second part is nothing but just a line segment connecting from 0 to y minus x. Okay. uh, so I'm sort of making, taking gamma, and I'm also pushing it with sort of with a line segment connecting from 0 to y minus x. So you see that, um, okay, so let me put a box around it. You see that when s equals to I, then that line segment, right, starting from s equal to I, the second part you see that is 0 when s equals to I, right? And then when s equals to t, oops, what I'm doing. And then when s equals to t, you know then s minus a over t minus a equals to 1. So that gives me exactly y minus x, right? So I'm correcting it, so okay, so you see that, gamma, I'm just rewriting what I wrote down there. So gamma y of a is just gamma a, right? And gamma y of t, so at t, right? So I'm gonna just have that is still gamma t here. And then, I'm adding the correction term, which is exactly y minus x, right? And this is just x plus y minus x equals to y. Okay. So I have created a sort of a new curve based upon gamma, and adding sort of a correction term, which is a, a line segment connecting from 0 to y minus x. By using that, I have created gamma that going from gamma a to y. And this is not the only way. You can also create other more complicated connections, but for my purpose, this is good enough, and this is the probably the easiest way to use gamma to create a new gamma y. Okay. Any question for me on this? Okay. Yeah. So similarly, that's clear, right? So I have that creation of new gamma y, and again, this is all up to you. Believe me, I have tried, and you can also try. You can create other curves as well, and this one is okay for my purpose, and that's enough. Okay. Uh, right, so I have a new gamma y, and you see that, I'm highlighting the one on the left now. It's exactly the thing that I have written down on the right. So this one is exactly that one. Okay. So this is great because so far I have been able to see that I have a new relation for the part gamma y, right? And you see that, the earlier uh, the earlier relations here, this one, this first one is the equality that tells me that, okay, if I'm going along gamma, I have the equalities and I can see everything through, you know. And the second one is giving me an inequality, but that is good enough because I can see that, you know. So the second one gives me that I have uy is less than equals to integral from a to t of L of gamma y, gamma dot of y ds plus c of t minus I. This is just a constant, don't worry about this, plus u of gamma I. So this is just a constant. Okay? I'm not worried about this. But this is good, right? Because it tells me that I can start seeing the value of uy floating around, right? I can now start compare the value of uy with the value of ux, right? Because when y equals x, I have equality, and y less than x, I have inequality. That's great, okay? And that's exactly what we do. Now we're gonna define this to be exactly a new function. The right hand side here to be a new function. Um, C plus. C plus because it's greater than equals to U, okay? So C plus Y, then clearly, let me just write down first, and I'm gonna discuss deeper about the C plus. So clearly, what do we have? We have that uy is less than equals to C plus of Y, right? Again, that's just a new function C plus, evaluated at Y. I don't, I don't know clearly what it is. We're gonna see it just in 1 minute. Um, and then x equal to y equals to x, we have equality. So that's remarkable, right? So geometrically, it looks exactly like the picture on the left panel that I'm highlighting now. And you know, for those of you who have worked on you know, nonlinear elliptic parabolic equations or with equation with maximum principle with viscosity solution, this is a very intuitive picture. But if you haven't done so, doesn't matter. It's really a nice picture having the function u, and you're touching it from above by a nice function c plus at exactly the point x. Elsewhere, it is greater than or equals to 2, greater than or equals to u, but at x, they are equal. So, you know, you can imagine that you have an object that you want to observe, and you have something, you know, touching it from above and touching exactly at the point x of observation. That's sort of, you know, that's sort of how we go from trying to observe uy for y near x to this new function c plus. Okay, and if you want to say it, write down clearly, you can write down to see that what is c plus, right? So c plus of y equals to, again, the definition is the left hand right hand side here. So you can just write down clearly integral from a to t L gamma y can be written down clearly, right? So I have gamma t plus s minus I over t minus I of y minus x. Oh, I should have written as this gamma s, I'm sorry. Gamma dot of s plus, if I differentiate in s, right, I'm just gonna have the slope is gonna be exactly y minus x over t minus I. That's the slope of our, you know, additional piece, ds, and plus a constant. I mean, the other pieces are just constant, plus ct minus I plus u of gamma I. Again, this is just a constant in y, okay? So now let me highlight where does y occur, right? Y surely occurs in the variable, right? In the Lagrangian term, it does occur in both the position term and also in the velocity term, right? That's it. That's all. And gamma is our given part, which is ck, right? You know, we have proved that any minimizer is ck, so that's good. I'm not worried about it at all. Okay. Now, if you look into this, you know, you see that we are integrating along gamma, which is already nice. And then I have some additional terms involving y. You see that you can differentiate the Lagrangian k times, right? Because L is ck. So as L is in ck, you automatically see that c plus is in ck, right? Because you can just differentiate as many times as you like, and I'll come back to this. Okay, so we get back to computing these dc plus of y later. Okay, it turns out that in this proof I'm being lazy, so I don't even need to compute what is the gradient of c plus of y. I'm just using the fact that, you know, it's beautiful that u is a Lipschitz function, right? Okay. So geometrically, you see that u might have corner like this. It just, you know, a zigzag function. This is u. It might have corners. But so far, you know, by using our method, we have been able to design a new function c plus that is in ck, is, you know, is touching u from above at the point x. Okay, so that's the geometric meaning. And you have seen that, you know, so far I'm using the information that I'm going from gamma A to gamma T. I'm approaching gamma T from the left, and using that piece of information alone, it's not enough. It helps me to see that I can find a function, a ck function that touching u from above at the point x, right? Now you can see if I'm using the other piece of information, if I'm using, if I'm using the fact that I can go from gamma t to gamma b, right? So this is the other piece of information that I have not used. If I'm using this sort of smartly, then I can get the other missing information, right? I can, again, geometrically, I can find another function, c minus, that touching you from below. Okay, so we're gonna now try to prove this picture. Let's just do it quickly, and we will be able to show that we have this picture I'm highlighting on the left panel, that beautifully the function u can be squeezed by one function from above, which is c plus, and one function from below, which is c minus, right? And c plus and c minus are both ck, and they squeeze the function u at exactly the point x, and this geometrically already gives me the point that u is differential at x. Okay, so let's do that now. Okay, now we're gonna approach see from the other side. I'm gonna just write out the formula quickly with you, and then we verify that. Okay, um, so we're gonna start from x, trying to approach gamma b, right? And again, the natural idea is that I'm gonna try to see if I'm in a point y, which is in the neighborhood of x. How do I go from y to gamma b, right? And this is the curve that I'm highlighting here. And to go from y to gamma b, I'm gonna use gamma, right? So I'm gonna define this new curve. And as I said, you can design many other curves as well. You don't have to be exactly this one, but this is I would say that the simplest one if we have to design, right? I need to use gamma, and then I'm gonna add a sort of a line segment going from y minus x to 0, right? What do I mean? At t equals to s equals to t, I have that this piece is going to be y minus x. So that allows me to have that gamma y of t is going to be x plus y minus x, which is y, right? And then at s equals to b, then the piece that I'm adding is just 0, right? Because it's going to be, going from y minus x to 0 at the end point is 0. So at the final point, gamma yb is nothing but gamma b. So that's good. That's exactly the curve I'm going from y to gamma b. Okay. And again, we realize the fact that we have, uh, u is dominated by L plus C. So I have, going along the curve gamma, the difference in the value of u is dominated by the action function of L plus C. So that's exactly that. And you rewrite it, you can see that you have u of y is going to be uh, greater than equals to the right hand side. So u is dominated, the right hand side, right? So sorry, the right hand side is being dominated by u. So I define the right hand side to be c minus, right? And you can see that, okay, again, y does occur in the position and velocity variable. I mean, you can see y here and y here. You can differentiate k times because L is ck. So you have been able to see that we have the function c minus, which is ck, right? C minus is always less than equals to u. And at the point x, the curve gamma y becomes just gamma, right? So I should have said that. So this is y, this is sort of like gamma y. So at y equals to x, and I should have that gamma x is nothing but just gamma, right? So that means that I have equality at x. So clearly that what is really beautiful is that we have created we have designed two functions c plus minus in ck, and that we have c minus is less than equals to u less than equals to c plus, and c minus x equals to ux equals to c plus x. Okay, so geometrically again the picture is that, so this is u, this is c plus, this is x, and this is c minus. Okay, so they squeeze the function at the point x, right? And you see that I'm being really efficient or lazy, depending on how we put it here, that I'm not computing anything with respect to C minus or C plus, right? I'm just saying that it's clear that they are CK. I don't have to compute their derivatives at all. But that's enough, right? Because remember that C plus and minus are CK function. If they are touching at the point X, then clearly I have that they are touching exactly the point x, so the gradient at the point x are the same, right? Because that's a geometric picture. In 1D, if you draw a tangent line here to to the graph, then it's exactly the tangent line to everything, right? Or if you want to write out a proof, you can say that so I'm writing that p equals to dc of c minus of x equal to dc plus of x, right? If you want an actual proof, you can see that since this is because, again, you can say that c plus minus c minus has a minimum at x, right? Because c plus minus c minus is always non-negative and is equal to 0 at 0 at x, so it has a minimum at x. So clearly you have the gradient of c plus minus c minus at x equal to 0, so we can just set p to be dc plus of x to be dc minus of x. Okay? And then you can do a little bit of Taylor expansion, or just write out the definitions of differentiability. So by Taylor expansions, you can expand your function out around at the point y near x. So that's the two lines that I'm highlighting on the left panel here. Okay. And because you can squeeze u in the between. So u is dominated by both c minus and c plus. Then I can wait. I think I made a typo here. So there was something that is about c. It should be about u. So because u is dominated, let me make a different color so you see that I made a typo. So then I can, because again, u is dominated by c plus and c minus. So when I'm squeezing u in the between, I can see that I have uy minus ux minus p dot with y minus x is going to be less than equals to an error term, right? This is from the Taylor expansion, and the modulus of continuity is just the maximum of two modulus. So therefore, by definition of differentiability, I have that it is not c. U is differentiable at x, and dux equals to p. Okay, so u and dux equal to p. Okay, and that's the proof. Yeah. So let me give a conclusion, and then we have time for discussion. And as I promised, I'm going to try to compute the gradient of c with you, which is quite fun. Okay. So this is, in a way, it's after all, we are dealing with calculus of variations. We are dealing with variations of curves, and we are dealing with minimizers. So in a sort of rough way, I would consider this method to be sort of like a variational method, right? So you need to do variation from both sides, and that's why I need t to be strictly between a and b. if I only have one side, so if t is equals to I or t is equal to b, then sure I can still decide something. You know, something that is sort of like touching you either from above or below, but that is not enough to conclude that your function is differentiable, right? For example, in this picture that I drew here, you know, if u is a zigzag function in this picture on, you know, like I'm putting a box around it here. If u is a zigzag function, it's not differentiable at the that corner from above, but you can still touch it from above by a smooth function. So touching it from above or below by smooth function doesn't guarantee us that we have a function is differentiable there. However, if we can touch it from both above and below at that point, then it's surely guaranteed. And that's, you know, exactly the proof by using sort of like um, tile expansions or modulus of continuity there. Okay, and that's sort of the idea. And I would say that how should I put it? You know, like this proof is quite generic. Later on, if you have ever seen anything like this, you know, in also either this context or in backward characteristics in PD context, if you want to give a proof that your solution to the PD is differentiable along characteristic, you can just, you know, modify this proof accordingly. So you're gonna have a whole natural proof, and this is why I think that is remarkable. Okay? Um, so I guess that we have, you know, let me copy C here. I promise I'm gonna do something, but I, you know, before, let me copy and then we have time for discussion. Uh, so any of you have any, you know, points of concerns or anything you want to discuss about this, or, you know, in general, you know, anything?
So it seemed to me that you don't really use the property of gamma in the new function C plus and C minus, right?
Yes. Yes. So that's a very good question. You see, so I'm using that. Okay, let's be careful. So let's say that I'm using implicitly here that gamma is ck, so that, you know, the curve is nice, right? Uh, you know, because if the second slot involving the velocity, if gamma dot is not too nice, then I would have to be a little bit careful. Although, you know, this is maybe not, it's not a big issue, but you're absolutely right in the fact that you see that, you know, this is a very how should I put it, uh a very weird proof, right? You know, I'm just touching it from above and below by two functions that are ck, and I'm done, right? I'm not using any property of gamma. Now I'm hiding here the fact that I'm using gamma in the first part to prove that the gradient is computable, which is du gamma equals to dv of L gamma dot, right? Yeah, but indeed you are right that uh, somehow magically I'm only using that I have gamma as a calibrated curve. Okay, so I do need the equality in one here, right? Without that equality, then I'm doomed. But yes, that's something that is really remarkable. Okay, yeah, but on the other hand, if you look into my book, then I'm actually using gamma, and I, thanks to that question, now I'm gonna do computation of the gradient of C plus, and you're gonna see that um, yeah, we we're gonna use gamma, right? So you know, so question, how to compute dc plus of y. I mean, this is not hard, right? You just compute by whatever product rule, chain rule. It's just depending on linearly on y here. And as I said, you can design more complicated curve that the slot of position and velocity depend on y in a nonlinear way. This is not an issue. So how to compute dc of plus of y, this is not an issue. Now, about certain question, this is, also how to prove this is not easy. Well, I goodness, how to prove that dc plus of x equals to dvl of gamma t, gamma dot t. This is a harder issue, right? Because we actually we proved in the proof that u is differential at x. That's the second part. I didn't compute du of x. I computed it earlier by using a different trick, right? So that's sort of like we have to do it two ways. And I realized this also when I was writing the book that there are many different ways to do that, and one way is actually we can compute the gradient directly. And let's do it, and you see that I'm gonna use the Euler Lagrange equation very very neatly here. Okay, so let's do it. Okay. So computation of dc plus of y. Well, again, I mean, the good thing is that the constant goes away. I don't have to worry at all about the constant. Just integral from I to t. Uh, the first lot is dx of L. Okay, I'm not gonna write out the slots because that's gonna be too long. If I differentiate in y, I should get, hold on a second. No, that's true. I should get, no, let me try to rewrite. This is not a good way to write it. I just get a scalar constant L, right? So it's s minus I over t minus I dx in L. Okay, evaluated at those, whatever. Plus the second term, if I'm differentiate also in y, I should get d no, also constant. Uh, Let me write in a different color so that you see what's the constant. 1 over t minus I dv of L ds, right? So that's a gradient. Okay, h of the dx and dv is a vector, right? So everything is consistent. Okay, let's pull the 1 over t minus I out. So this is this integral from I to t s minus I dxl plus dvl ds. Okay, this is the best I can do. I mean, that's pretty much it, right? Again, correct me if I'm wrong. I mean, I'm trying to I might made a mistake. I'm trying to compute it with you now. Okay, so that's good. I'm done with the first part. It's just a simple computation. Again, it doesn't reveal anything yet. But now add, let's compute at y equals to x, right? That's the point of concern, because at y not equals to x, I don't know, right? I just have that is sort of like greater than u for C plus. So at y equals to x, what is dc plus of x? When y equals to x, and I don't have this, I don't have this variation of my curve, right? When y equals to x, then all those variation terms go away. So I only have that dc plus of x equals to 1 over t minus I integral from I to t. Let's see, this is s minus I dx L of gamma dot plus dvl of gamma dot ds. Okay, again, nothing, right? This is just that. Now recall that gamma is a minimizer. I'm now going to use Euler Lagrange equation, right? That's sort of something we haven't used. Okay, so as gamma is a minimizer with two fixed endpoints, gamma a and gamma t, right? So we have gamma satisfies the Euler Lagrange equations that I have what? D over ds of the VL gamma dot equals to dxl of gamma dot, right? For a less than equals to s less than equal to t. So that's what I have. Now I can plug this relation into the earlier into this one, right? What can I do? I can replace dxl by d over ds of dv, right? So that's let's do it. So then I have dc plus of x equals to 1 over t minus I integral from a to t s minus I d over ds of dv l of gamma. Let's put s here so that you'll see gamma s gamma dot s plus dvl gamma s gamma dot s ds. Okay, now magically you see here this is nothing but this is exactly the product rule. Okay, right? This is the product rule. This is just d over ds of the whole thing, s minus I dv of l of gamma s gamma dot s. Okay. Yeah, so it's really beautiful, by Euler Lagrange. And here we are really using, it's a minimizer. Well, I mean, explicitly because we have to compute explicitly. So it becomes the full, derivative of a function, right? And so, okay, let's just write down. So it's 1 over t minus I integral from a to t d over ds of s minus I dv l gamma s gamma dot s ds. And now we are just using the fundamental theorem of calculus, right? So it's equals to 1 over t minus I, the difference of the two ends, right? When s equals to I is just 0, right? Because so the only the upper upper end matters. That gives me that is t minus I dv of l of gamma t gamma dot of t. The t minus I cancel out, so we get exactly the conclusion. This is I don't know, a harder way to go through it, but it's really worth it. I don't know. To me, it's really beautiful. I mean, so that's the end. Yeah, so you see we can prove the whole theorem directly by only using part 2, and we do sort of direct computation in which we use the Euler Lagrange equation and minimizer directly, or else you can see that in earlier part we only use that they're touching and we prove that it's differentiable, and then we use the part 1, part 1, and this one goes to duality and blah blah blah, to get that the du of gamma t is exactly dv of l of gamma t gamma dot of t. So I would say that this proof, the later part I just added here, it's a little bit more sophisticated, but on the other hand it's also very natural in the sense that I just need to do computation, and I'm always mindful of the fact that I have uh, gamma is a minimizer, or it's a solution to our Euler Lagrange equation. Either ways, I don't know. It's really neat when we see it this way. Okay. Any concerns or anything of discussion you want to talk about? Yeah, so I mean, I guess that we can end, and thanks a lot for always that for the discussions, and I think that you guys did pay a lot of time to think about the class. One way or the other, I don't know. I mean, there are still a lot of things that are being sort of study and being considered at this moment. Uh, for example, if you do this one in a non-compact setting, it's really hard. Also, there are people who have been dealing with infinite dimensional spaces. This couldn't be easy at all. What I'm doing here is still the basic one, but again, remember that this whole theory, the book and everything were written down not so long ago. So I mean, the tools are pretty much, you know, in a way, simple but fundamental. And I'm hopeful that one way or the other you can use it. You know, also for me, sometimes I'm able to use that. I'm really happy, but sometimes it's just like you know something for us to enjoy, right? Other than that, and again, I mean, take it easy. I'm hopeful that yeah, uh, things gonna be better and better as time goes. And let me know you have more concerns or questions. Okay, so let's stop now. I'll see you again on Wednesday. Thank you. Bye.
Thank you.
Thank you.